Hi, I'm Chris with Sanderson Test Prep, and in this video we're going to take a look at another example of finding extrema. So we're looking to find our local max, local min values, as well as our absolute maxima and minima for a given function. And here we'll take a look at this example. So we see f of x equals 1/3 x cubed minus 5/2 x squared plus 4x. And they're asking us to evaluate this function across the interval where x is between 0 and 5. So let's take a look at how that's going to work in terms of finding those extrema. So if we remember from the last video, to find your extrema, first you take the first derivative of your function, and we're going to set that equation equal to 0 to solve for those critical points. So the first derivative of this function, we apply power rule, and we would get 3 times 1/3, which actually we can just simplify that. 3 times 1/3 will just be 1. So this will end up being just x squared minus, and when we multiply by 2, we'll have 5x when those denominators cancel. And then when we take the derivative of 4x, we just get 4. So we have x squared minus 5x plus 4. And we're going to set that equation equal to 0 and solve. And luckily, for this one, it does happen to factor. So that makes things kind of nice. We have x minus 4 and x minus 1 as our two factors. And so our critical points here will be when x equals 4 and when x equals 1. Okay, so now we have to determine, our next step is to see whether those critical points represent a local maxima or minima. And to do that, we want to look at those values along a number line, and we want to check the slope. Let me leave a little bit more space here, but we want to check the slope on either side of these values. So for 1 and 4, we're going to check a point somewhere in here, less than 1, and then somewhere in here between 1 and 4, and then somewhere over here greater than 4. So let's see what that will look like. So easiest thing to do is try to use numbers that are going to make the math as easy as possible when you go to plug it into your first derivative equation. Remember, that's where you're plugging it in. A lot of people want to plug it back into the original, and we will do that when we're evaluating whether we're looking at the local or absolute maxima or minima, but right now it goes back into this equation here. So let's try 0. If we test out 0, it makes the math easy and quick. 0 squared is 0, minus 5 times 0, which is also 0, so we just get 4. That's a positive value, which means we would have a positive slope leading up to that first point. And then if we plug in a 2, so 2 squared is 4, minus 5 times 2, so 4 minus 10 would be negative 6 plus 4 would be negative 2 for our total, so it's going to be a negative value. So it's going to be negatively sloping in between 1 and 4. And then on the other side of 4, if we plug in a 5, so 5 squared is 25, minus 25 would be 0 plus 4. It's positive sloping again there. So hopefully you can see even visually, and sometimes I recommend when you're first getting comfortable with it to just kind of connect those arrows so that it is a little bit easier to visualize. But this would be a local max at point 1, and this would be a local min at point 4. Now let's test across our interval whether or not those values are in fact representative of the absolute max or absolute min in that interval. So here, if we want to test that out, we can take our x and y values for the ends of the interval, the critical values, on the other end of the interval. So we're going to test all 4 of these, all 4 values, to see what value we get for the function for each of those. And when you test all 4, a lot of times you'll see it set up in an XY chart where we can test out each of those values. So we're going to test the 0, the 1, the 4, and the 5, and we're going to see whether or not we know that when we tested this out, 1 was a local max, but maybe it's the absolute max, let's see. 4 was a local min, but maybe it's the absolute min, let's see. So if we plug in a 0 into our original function, so now for this part, it's really important to know. Let me see if I can minimize this enough to draw an arrow, but now we're plugging back into that original function at the beginning. So here, when we go to plug back into the original, if you plug in a 0 for x, and I'm just gonna copy this function and paste it down here so that we can see it right next to the calculations that we're doing. So here, if you plug in a 0 for x into that original, you'll come up with 0 for y. If you plug in a 1, you'll get 1/3 minus 5/2 plus 4. And this one, just because it's a little bit more complicated, I'll write it out. Multiplying by the x is the easy part here, but we're going to have to find some common denominators. So that would be 2/6 minus 15/6 plus 24/6. And so that would be negative 13 plus 24 is going to be 11/6. When we plug in a 4, so here f of 4, we're going to have 1/3 times 64. So we'll get 64/3 minus 5 times 16 would be 80/2, so that'd be minus 40 and plus 16. So that'd be 64/3 minus 24, which is same as saying minus 72/3, so we would get a negative 8/3 for f of 4. And for 5, we see the work there on those. I'm going to go ahead and delete this for now. And for our last point, to check the other end of our interval, we do f of 5 would be 1/3 times 5 cubed is 125, so I'm going to shorten this up and just write 125/3. If you have questions on any of the algebra, you can always pause and do the math on your own and double check your work. Here, this would be 5 times 25, which is also 125, so this would be 125/2. And then plus 4 times 25 would be 100. You have to find common denominator here, which would be 6, so you get 250/6 minus 375/6 plus 600/6. And when we go to add those up, 250 minus 375 is negative 125, plus 600 would be 475/6. And so we can see here in doing this calculation that for our minimum value, this is our minimum value both of the critical points but also within the interval as a whole, which means that the negative 8/3 at that point when x equals 4, we already knew that it was going to be at least a local min, but this actually ends up being our absolute min of this function within that interval. Now when we check these endpoints, what we notice here is that 475/6, the endpoint at 5, is actually a higher maximum value. So even though at 1, when x is 1, we had a local max, it wasn't our absolute max of that interval. Within that interval, our absolute max occurred when we got this higher value at the endpoint when x is equal to 5. So this would be our absolute max in that interval. And that's it. So we found our critical points. We tested our critical points and our end points to check and see whether our local mins or local maxes were in fact absolute mins or absolute maxes for the interval given. For more, please check out our other videos, and thank you.